Thanks for the invitation. So it's a pleasure to see everyone there, although I'm not in person. Today my talk is going to be about the behavior of the time constant in high dimension. So actually, my recent research focus has been shifted a little bit away from first passage, but I still decide to give this talk because it's more relevant to the workshop, I guess. So this is based on a joint work with Antonio Alfinger and my student, Chen Kun Guo. Since I bet everybody has known enough about the setup of FPP, so let's just quickly set up our definitions and assumptions. Okay, so it's standard FPP model on ZD, where we define passage times as non-negative random variables, IID, for each edge. And then we define the passage time for each path gamma, which is the sum of all the passage times along the path. And the first passage time of any 2 points on the integer lattice is going to be defined as the smallest passage time for the path connecting these 2 points. Of course, this can be extended to any 2 points on the RD, the real numbers, if you consider the lower left corner. Okay, so the next thing we want to define is the ball of radius t, which is all of the points that can be reached by time t for all the real numbers of RD. Okay, so that's just standard. So we are mostly interested in the time constant behavior when d gets large. So we want to define the time constant first. So throughout this talk, we will always assume the passage time has a finite expectation. So with this assumption, the limit as n go to infinity, if we go from the origin to n times any vector in the in RD divided by n is going to have a limit, and we call this limit the time constant. And the famous shape theorem says that, well, if we have additional assumption that the point mass on 0 is not too large, and we're approximately having a shape, and the shape basically defined by the ball of radius t normalized by t is going to convert to some deterministic convex and the compact set, which is non-empty. Okay, so that's what we know. I think everybody knows maybe from last week's introductory lectures. So a picture for the limit shape is the following. We look at bt divided by t, and in the limit is going to convert to some this deterministic shape. So I just want to mention two things that we will use in terms of the scaling. The first is that if you think about time constant as the time per distance v, essentially, and the limit shape, if you look at it, is the distance per unit time. So you can kind of see that along the E1 direction, the limit shape should have a radius, or maybe I shouldn't call it a radius because it's not a ball. So should have a distance in the E1 direction 1 over mu d of the E1 direction. So that's the relation of the limit shape and the time constant. So essentially, if you can say something about the time constant, you can say roughly the same kind of things for the limit shape. Okay, so the thing I want to focus on today is the high dimensional behavior, and I want to list a few results that we already know along this line. First is the one by Krishnan in the 84. This is the monograph called Aspect in First Pass Percolation. That says that, well, if I have finite expectation and some nice behavior that I will explain a little bit later for the passage times, then roughly in the E1 direction, I should expect the time constant behave just like log d over AD. So this is as d go to infinity. So the limit mu d over log d times AD converges to some, well, this result is not yet convergent, but it tells you the order of the E1 direction in terms of the time constant. So later, Dar improved this, well, actually proved a special case of exponential passage times that says, well, if I consider the time constant to be exponentially distributed with some number a as the parameter, then I could show this time constant along the E1 direction is roughly following the scale of log d over 2AD, and especially the mu d E1 divided by the right side is converging to 1. So that's what this symbol means. And then we later generalize this result to any distributions essentially that satisfy both of these. And we show that not just for exponential, but for any distributions, it will also have this limit as they go to infinity, basically. So so the thing is that, well, if you look at this condition, basically it says that the distribution of tau e is going to have a density a at 0. Okay, so this requirement is including a lot of the distributions, like exponential, like any continuous distributions with a density, as long as you can have a density at 0. So I'll comment a bit later that this is a very important feature for the high dimensional behavior. And the exponential case is just a special case for the finite expectation and the density at 0. So later a result by Martinson that says that, well, as you can say, you can see from what we have discussed, if you want to say something about the limit shape, having only one direction is not enough. You just know the scale in the E1 direction is not going to tell you anything about the limit shape, whether it's a ball or a diamond or anything, or L infinity ball and things like that. So you need at least another direction. So the Martinson's result says that, well, if we consider the diagonal direction of 1, 1, 1, 1, 1, if you compute the time constant along that direction, as they go to infinity, this time constant is converging to a constant. Okay, as they go to infinity. And this constant is specified by, well, of course, this A is the same as the density A over here. And the beta square, beta is a constant, is square root of beta minus 1, and the beta solves this fixed point equation, hyperbolic cotangent beta equal to beta. Okay, so that's what we know so far about high dimensional time constant. I think no more than this, even today. So this latest result is in 18. So the question following this is that, well, what does this imply for the limit shape? And how about the time constant asymptotics in other directions? So as we know the time constant in more directions, we can say more things about the limit shape, essentially. So but the first thing I want to discuss a little bit is that, well, when we know the scale of the time constant in the E1 in the diagonal direction, and when we know the time constant in the E1 direction, we can eliminate a few candidates for the possible limit shape. So as I said, the limit shape B has a length equal to 1 over mu E1 on the E1 direction. So if we just rescale it to make it just touching this point, we can say we can try to compare the time constant in the E1 direction and along the diagonal direction. So first, Martinson's result suggests that on the diagonal direction, so this point here, roughly the time constant is beta squared minus 1 square root over 2a. But on the E1 direction, is log d over d scale. So meaning that it's going to take much longer to reach this point on average than to reach this point. So this will tell us that by comparing this number and this number, for d very large, at least I will know this number is going to be greater than this number. So the limit shape is going to be contained in this L infinity ball. So it's not going to be a L infinity ball, not equal to a cube, essentially. So further, if I rescale this, so we all know the scaling of the time constant. So we rescale this point to the corresponding point on L2 ball, meaning that I'm dividing everything by 1 over root d. Then I can see that this time constant should behave like the same number divided by root d. I think this is elementary, but still this number is bigger than the scale on the E1 direction. So meaning that still this number should be, so this point should be outside the limit shape. Okay, so for d sufficient large. So this number, when d is sufficient large, is going to be eventually smaller than this number. And that also tells us that, well, the limit shape rescaled in this way that touching this E1 direction is now going to be an L2 ball because this 2 point at least won't overlap. But it cannot have this direction because even if this point is here, I could still have, let me just try to draw that, some shape that is, let me just try to maybe maybe draw something like this. I'm not sure, like this and this and then this. That will intersect with the L2 ball, so you cannot have the contained direction. And furthermore, if you keep shrinking this vector on the diagonal direction, you can get consider the point over here, which is essentially 1 over d, 1 over d, and 1 over d over here. And we know that in this case, the time constant in the diagonal direction is behaving like 1 over d, which is eventually being smaller than the time constant on the E1 direction scale. For the sufficient large, that means this point, purple point, is going to be inside the limit shape eventually for the very large. And since we have convexity and we know that this limit shape is going to contain the entire L1 ball. So following the same strategy, you can actually eliminate all of LP balls. As possible limit shape for the FPP, right? So I think the factor that making us some trouble is this log d. So however you want to look at this diagonal direction, you rescale it, you're not going to have the LP balls eventually because of this log d. Okay, so how this log d arise? That made us to further consider how when moving from, let me just go back a little bit. When moving from the E1 direction, which is 1, 0, 0, 0, to this direction, which is 1, 1, 1, 1, 1, 0, the scaling is changing from log d over d to this constant number by increasing the number of ones in this vector. So we've recently tried to compute any directions for a general setup. So basically, we look at any number of ones combining with any number of zeros. And we'll call this ones is going to have FD coordinates. And the rest of the zeros will have d minus FD coordinates. So this is the middle case between the diagonal and the E1 direction. So we can actually compute this direction, and we get asymptotic for this particular setting, which involves the Lambert W function, and it's going to behave like this. So of course, I assume FD over D has a limit, otherwise you cannot take the limit as D goes to infinity. So the Lambert W function is a special function. It has, when you consider the input of this function as a complex number, it has many branches. But if Z is a real number and also positive, it will have only one output, basically. So it's giving you a number. So you give me a Z, which is non-negative, and I'll tell you what is the W that satisfies this equation. So let me draw a little bit of this function. So when Z is 0, and WZ is going to be, I think, 0, right? 0 times e to the 0 is equal to 0. So the behavior is like this. So when Z is super large, very, very big, basically this W does not play very much role over here, and we essentially get W is like log Z. So the asymptotic for this function is like over here, it behaves like log Z. And near 0, it behaves like X, like Z, sorry. So near 0. So then we can try to see, well, what does this tell us? Well, if I have FD is a smaller order of D, so eventually the one fraction is not going to be proportional to D, then I know D minus FD is roughly just D, and FD, D over FD is just going to infinity, and this part is going to look like log D over FD. Okay, and this part, that's going to give you this part, and the front factor is going to behave like D over the FD while I'm moving the numerator FD to the denominator. So that matches the mu E1 case. Mu E1 case is just FD equal to 1. I just have one coordinate that has non-zero entry. And the next thing is that, well, if FD is a proportion of D, meaning that this limit converges to some alpha strictly between 0 and 1, then I will know this is going to converge to 1 minus alpha over alpha, and this is still a constant. And this part is going to converge to alpha over 1 minus alpha if D is sufficiently large. Then the time constant in the limit as D go to infinity is going to behave like this order 1 constant. So let me just finish talking about the last case. So in the Martinson's case, I have every entry being 1. Okay, so in this case, is it corresponding to the alpha equal to 1 case. Okay, and by sending this function as alpha, sending alpha go to 1 and look at the limit of this function, I will have essentially, because the WZ is behaving like Z when Z is near 0. So this will tell me the limit of this constant is going to behave like this. So this is the corresponding to the diagonal case of Martinson in 2018. So so this actually explains a little bit why we have the log factor. It's this Lambert function having different asymptotics near 0 and near infinity. Okay, so also there's 2 cases. So the case when I have a vanishing fraction of 1s and the case when I have a constant fraction of 1s are going to proof in different ways, actually. So I'll show you a little bit the strategy in these proofs for high dimensional result, because I think well, as the purpose of this workshop, maybe some of the techniques can be useful to solve other questions like high dimensional, maybe geodesic, or high dimensional behavior of other quantities of FPP. So next I will talk about some common techniques we use specifically for high dimension. So, but I just want to list this result to show you how we can unify all of the result on this, on this page by this Lambert function by considering the E1 direction and intermediate case between the E1 direction and the diagonal direction. Okay, let me just go back to the slides. So there are a few things that's very special for high dimensional behavior. The first thing is that we don't really care too much about the distribution of tau e, the passage time. This is because when I have a very large d, it's very likely that at every step I'm going to have a very small passage time. So if you want to reach some faraway point, essentially, if this point very far away is not too far away comparing to the dimension, it's going to be essentially behaving like every step toward that point, you look for the smallest passage time. So that's essentially the behavior. So when that happens, you have so many choices in each step, meaning that it's going to be very, very likely that you have a very small passage time. So the passage time the behavior of the passage time near zero is critical. So whether it's having this density or having maybe this density, it's not going to be that important as long as I know there is a small window that has a density for this tau e. So for this, this is one fact that we use many times in the proof. So once we have the kind of universal property for the passage times, we could just focus on some special distributions. Essentially, it's enough to consider just exponential distribution. And the A part over here is not that important because the exponential has the scaling property that you multiply A, it's going to give you some different exponential. So then this is a nice property because when we consider exponential passage times for the FPP model, you have Markovian, you have many nice things for the FPP model. So, and you can have memoryless property and so on. And once we focus on the exponential distribution, we could explicitly compute, say I have a path of length k, and I want to know what is the probability of this passage time less than or equal to some x. And this is exactly a sum of exponentials, which is gamma. And gamma has an explicit density that you can compute. So you can approximate that very nicely if you have if you look at small x, and you can approximate that nicely with x to the length of this path and the factorial of the length of the path. So that's one thing very important for the high dimension. If you have low dimension, this is generally not true because I really need to consider how E behaves far away from zero. So that's one observation. The other observation is that when in high dimension, basically when I consider path of from simple random walk, as long as my path is not going to be very long, say smaller order of d, less than root d essentially. So if I look at the path of length n, which is on the order of log d, then all of those paths are going to be self-avoiding. So because you only go that much in the path, random walk path, and you have a d dimension, basically every step you are not going to repeat itself. It's unlikely. And almost all the random walk paths are self-avoiding and they are non-overlapping. This gives us some nice tool because we can now use a very nice second moment method to consider two paths at a time, and also some nice results from high dimensional random walk. And we can also enumerate most of the paths in the computation. And we can use a very nice union bound, which works nicely when I know the path will have very nice properties. So these are the two key observations in high dimensional FPP proofs, which I don't think they are true in the low dimensional case in general, but can be used for the high dimensional computation. Okay, so any questions so far? Okay, so interrupt me if you have any questions. So when proving the time constant, we aim at both the upper bound and lower bound. The lower bound is not so hard. So if you want to show that mu d, my computer just jump out some notification. So if you consider you want to show mu d is greater than something, okay? So we want to consider, well, for very large d, eventually the time from 0 to some to the plane that containing that point and orthogonal to that point is going to be summable as n summable in n. So let me just explain a little bit more. So if you look at the time from 0 to nv, basically this is approximately the same as the time from 0 to the nth hyperplane containing v. So that's the point to point time constant is roughly, let me just do this, the same as the point to plane time constant. Okay, so then we can consider, well, if I have some direction v, which is diagonal or the sub-diagonal directions. So this is my E1, this is my EFD, and this is a diagonal defined by E1 and EFD. So I could look at all of the paths. So I could look at this particular quantity that going from 0 to n of v. Here, let me just erase that. So with this, if it is less than infinity by Borel-Cantelli, and the summation tells me that this time constant in this direction is going to be less than or equal to x only finitely many times, meaning that the time constant should be greater than that x. So I should remove that d. Okay, for large d, and this will show me the lower bound for the time constant. So essentially, this is just direct computation in order to get to this hyperplane Jn. What I can do is, well, I can spend some time in the rest of the directions, EFD plus 1 to ED, and spend m steps here. Okay, and then going through any of those directions from E1 to EFD is going to make me closer to this point. So this is just, to compute this probability is just enumeration. I look at how many ways I can get from 0 to this plane by spending m steps in the useless directions and k steps in the useful directions toward that hyperplane, and compute an estimate of the number of paths going there, and compute the probability of that particular path of that length m plus k is less than nx. And by plugging the time constant that we just computed in the theorem, we can show that this is summable. And we use explicitly the fact that this probability is roughly nx to the m plus k over m plus k factorial that we use for the gamma distribution. And we can also see that there is a lot of the cancellation by estimating the number of paths and the probability right here. So if you believe me, just plug in that number we proposed at the beginning with that Lambert function. You can do you can show that this probability is summable in M. So that's essentially the lower bound. Lower bound is usually not very hard, and especially you just concentrate on the exponential distribution and the gamma distribution. Okay, so that's the lower bound proof. The upper bound proof is a little bit different with the two in these two cases. One is the let me just rewrite the vector v, which has 1, 1, 1, 1, 1 over here that has fd copies, and 0 over here that have d minus fd copies. So in the case when it has a smaller order of d for the 1 entries, essentially, if you want to prove using the strategy that how you can get to this point by searching for a very efficient path. And when you have the V that has almost all the entries being 1, let me just say if Fd is a fraction of D, then you don't have that much space to search for a nice path. So let me just explain a little bit more about this point. So I want to show an upper bound for the time constant. And let me just draw this picture. This is my E1 to EFD direction. And I have a direction V over here. Okay, so there are some directions that will lead me directly to the first hyperplane that has, let me just say, this is exactly E1 over here. This is exactly EFD over here. So the first hyperplane is over here, and V is the point with the ones in front and 0 over there. So essentially V is in the hyperplane of HFD, because the sum of those entries is equal to FD. So I want to get to this hyperplane very efficiently. And well, as I said, the time constant is the time per unit per distance of the vector V. So I need to plug out the factor outside and then consider how we can get to the first hyperplane efficiently. So this is my H1 hyperplane. So the thing to do is that, well, if I take any of those steps, I will get to H1 immediately. But that will only give us a factor of 1 over FD, because I just look at the smallest one going there, and the minimum of the exponential of FD exponential, it will have a mean 1 over FD. So, which is not enough. So the essential strategy is trying to search for a nice path. So I just want to draw a little bit the other directions. Let's say this is E of FD plus P plus 1 and E of D. So I already know this directions will lead me directly to H1. And I want to consider some ways to search. So there are many ways that I can search for a nice path and in a subspace of dimension P. So the thing is that I start from 0. I can go in one of those directions and then search in a subspace of dimension P. And if there is a very quick path, and then I will move over here directly to the first hyperplane. So this is some very efficient path. And if there isn't a very efficient path, by searching in this dimension P subspace, then I will just move directly to the first hyperplane. So this will give us a very nice upper bound for the time constant for the passage time to the first hyperplane. So if I have a nice path that has a very nice time constant, then I will just go directly there. And this delta just compensates for the first step. So if the first step is small, meaning that over here I have a small first step, I have a nice path leading me to the first hyperplane, I'll just do that. And if I don't have this nice thing happening, I'll call this a good path. And I don't have, or I don't have a very small first step, then I just take the whatever the smallest one in those directions. So that one will have on the order of FD over the some tau expectation. So with this, if I can choose the space to search nicely, and I could make this whole thing just look like the desired time constant that I want. So in particular, in this case, we choose, so these are the remaining dimension that I can search for good paths. And if I want to, sorry, this is Cassidy that I want to aim at. So if I want to search for good paths of this scale of time constant, so remember that we are looking at FD over, FD is a smaller order of D, then the time constant is roughly looking like this times FD. But I just rescale that so I don't need to worry about the FD factor in front. So with this setup of the search place, a search space, and the desired time constant that I want to prove, we can show that as long as I have a positive probability to look for this good path that lead to the first hyperplane in a passage time that's very small, then I can show that the passage time is no more than this epsilon d, and as I send delta to 0. And then after rescaling, it should recover the time constant that I proposed at the very beginning of the theorem. So the rest thing is to show that why we can find a good path over here that has a length n, that I will decide this what is this length n that I want to decide to have a very efficient time constant. And this will happen with positive probability for all of the d. So this is just a standard second moment method. If I want to show some probability is greater than 0, I can use Cauchy-Schwarz, a special case of Cauchy-Schwarz, to compare the moments. So if I can find a path, meaning that in this nice set that the first steps using this search space and the last step leading me directly to the first hyperplane, and I can find one path over here, then my good path will be found. So this probability is bounded below by the expectation, the first moment squared divided by the second moment. So those two, as long as those two moments are comparable, then I will have a non-vanishing probability for this good path to happen. So let me just explain intuitively why this thing should be the case. So the first moment is essentially enumerating how many paths that I am considering times the desired event that I want that to happen, which is having a small passage time. And the second moment, if you look at that, is going to consider basically summing over two paths at a time. But as I said, we are in high dimension. So as long as I'm choosing the length of the path not too big, then these two paths essentially are not going to overlap and are not repeating itself. So those two things are essentially independent, roughly speaking. So then, if we are able to split this probability into two probabilities, then this sum is just like the first moment square. So in this way, that I can show that the second moment is comparable to the first moment square, because the paths are short relative to that dimension. So that's essentially how we prove the case when this number of ones is a smaller order of D. So this will leave me a lot of the space that I can do to search for a good path and then cross. And then the last thing I want to comment a little bit is about the case where you have a linear fraction of D for the 1 entries. So this is this cannot use the same strategy, but the thing is that so if you remember how we choose the dimension of the subspace is essentially D. So if I have a linear fraction that's already the 1 entries, so I could not have enough space to search for a good path and then cross. Even if I'm doing the same kind of computation, this proof will not go through. So there are not enough free dimensions. So for this case, this is actually our Martinson's idea. Let me just show you the alpha equal to 1/2 case, because other cases are similar. So the V in this case will have half the entries 1, half the entries 0. While for simplicity, let's consider 2D dimension instead of D to avoid taking the floor or ceiling of those of those numbers. Okay, so if I want to compute the time constant in this direction by looking at the probability of this type. So from 0 to this V less than or equal to T, then I will have a natural upper bound for this probability. So from 0 to V, if the passage time is less than T, that means at least there is one path that's connecting 0 to V that has a passage time less than T. But I can go through all of the paths and use a union bound, and I know this is just the gamma probability that I show you in the 2 key observations. And then this can be considered as a generating function in terms of T. It's a infinite power series. So then using some generating function techniques, it can be decomposed into some smaller dimensions. So essentially, if I'm looking at this sum, it can be written as the sum by looking at the path in Z2 that lead from the origin to the 1, 0 direction. Basically, I'm associating 1 and 0 at a time. So this tells us that in the case that I have a linear fraction of ones, the paths are basically trying to realize one coordinate 1 at a time. So if you roughly think about this, raising to the D's power is like I go from 0 to 1, 0, 0 that achieve index that achieve a coordinate 1, and do that again and achieve another index 1, and so on. This basically tells us in the high dimensional case, when there is a linear fraction of ones, it's like exploring the space, like and going along one direction at a time and independently, both basically like that. So Martinson's proof essentially shows that, well, if I can find a T star that makes this say less than or equal to 1, or especially less than 1, then this part is going to decay exponentially, and this will give me a natural bound, this T, for the lower bound of that, because the less than that T star is going to have very small probability. And in the case of the Z2 cross Z2 gets me Z2D case in this particular setup, that I can see that this T star that makes this just below 1 is going to be the limiting time constant scale. So it actually proves using the combinatorial and generating function technique to show that the T star that makes this sum equal to 1 is going to be the limiting time constant for the passage time for this particular direction of a linear fraction of ones. So what we did is trying to see, well, if I have any fraction D that are ones and the rest are zeros, how we can determine the critical T. And it turned out to be that Lambert function that making this quantity exactly equal to 1. So I think that's, I should stop, and that's the end of all of the things we know about high dimensional first passage percolation in terms of the passage times. So of course, if this will allow you to do the computation on other directions, it's just going to have more computation, but you can basically derive the time constant in any directions using similar technology. So I think that's the end. And if you have any questions, I'm happy to answer those.
Any questions for C? Oh, there's YKid has a question in the chat. Go ahead, YKid. Oh, could we open the chat window actually? Thank you.
Yeah, I can see the question. So when the increment of the support of tau e is not 0, say some b greater than 0, then result will not quite apply. In general, I don't think so. You're saying that if we just shift the distribution, whether that will still work, the whole thing will work. So in general, so if you consider the FPP model adding a constant to all the passage time, it will change the geodesic and the behavior very dramatically. So if you add some constant, then the passage time will be in favor of the short path, right? So short path will have at least it's not likely that you can look at many like the technique that we use here to for the results from the high dimensional random walk, things like that. So I don't think this is true.
Yeah, it seems like an interesting question then.
Yeah, but maybe you can, well, maybe in the exponential case, you can do some explicit calculation. But again, the thing is that you, well, I think the density near the B would matter. Only that part will matter because you still want very small path. But then it also depends on how the length of the geodesic behave. So it's not quite straightforward to see how this thing will go. But yeah, that's an interesting question.
Yeah, thanks for the question, YKit. Do we have other questions for C? I guess
I have a question.
Oh, yeah, go ahead.
So it sounds like you were saying, well, you said that the limiting ball as d goes to infinity is not LP for any integer p, and I think you were also saying not for any real number p. Is that right?
I think so. It's, well, because no matter how you choose that p, you are not going to get log d factor anyway.
Right. Okay. So yeah. LP, if it were LP or the Euclidean ball or something like that, that has a nice meaning that sort of is the same meaning across all dimensions. Is it possible that there is some other sort of description for the limiting ball that could be true across all dimensions? And would you have any sort of a conjecture for what that could be, so that you would be able to talk about directions other than the ones that you've studied here?
So like what kind of?
I guess, do you have any conjecture about what happens in directions that aren't just ones and zeros? And is there some way to describe that? I mean,
yes.
LP would be a nice way to describe sort of what happens in every direction, but it's not that. So is there some other way to describe something like that?
So actually we were working on the even more general direction. Think about, let me just find maybe some place to write. Maybe the last slide. Okay, I have some space to write. So if you think about any direction V that has, say, 1 and say 2, 0, like this, or 1 epsilon like this. So this is like a finite case, but with a little bit deviating from the E1 direction. So you can still do a nice lower bound, which is not exactly like what we have before, that you have some V directions that in the middle. So anything you go through this E1 to EFD direction will contribute the same way as moving toward along the E1 direction. Sorry, not moving along the V direction. So it's going to be using the result of more general random walk result. So essentially the V in this case. Let me just draw a little bit picture. Okay, and maybe the V is over here, and then you're going through this useful direction is going to contribute differently along the E1 direction. Sorry, along the V direction. So it's a random walk of general step distributions, basically. So you can still do a lower bound using the same kind of estimate, but for the upper bound case, it's going to be a more complicated. So remember that this is like FD is smaller order of D case. So in this case, when you do an upper bound, as I said, in this, you basically follow a search and cross strategy. So, but in this case, let's say if I have 1 and 2, so this part, and once you look for a very good path, and then it's going to be comparing that going to the first hyperplane, whether it's better to use this step, or this step, which is 2 steps versus 1 step. So then you need to compute to compare a little bit which one is faster in terms of exponential and the gamma 2 distribution. So it's in this case, it's really case by case. But it's possible to do that for the more general directions which is not ones and zeros. Does that answer your question?
Yeah, okay, thank you.
So the upper bound is going to involve more computations, but it is still doable. But just you need to have a nice way to say, well, what is this gamma distribution comparing with exponential distribution? And the observations still hold that you just need to consider exponential distributions, and you just need a very nice estimate of gamma and exponential distributions. You can still use the property of non-overlapping paths and self-avoiding paths and things like that. But it's, well, we certainly don't want to do that case by case, right? So then you can kind of get an idea, say in the limit shape, okay, there is E1, and whether, how, say for a large D, whether the shape is going to behave like this or more behave like this for the large D. So you can kind of estimate how different in the E1 direction comparing to the E1 perturbed a little bit direction by doing the computation. Does that make sense?
Yeah, okay, so you're able to get some differentiability results from that?
I don't think so. I don't think it's differentiability because if you want to get differentiability, basically you want this to go to 0, right? But the
Yeah.
estimate also require larger d. So you cannot do a fixed d and letting epsilon go to 0.
Right. Okay.
Yeah.
Thank you.
Yeah, but you can kind of estimate how this this part is different from a straight line, a little kind of, but not really differentiability, I think.
Yeah, okay, thank you for the question. And oh yeah, Shao. Oh.
I just have a silly question, but in this case, when we're working with this V, I guess somehow just looking at, let's say, mu of E1 plus epsilon times mu of E2 would also give us upper bound, but somehow this upper bound is just like, I guess going through the proof will give us like a sharper one. Is that
You mean like mu E1 plus epsilon mu E2?
So
like
that's
this?
upper bounds mu of V.
Yes.
I guess then going through.
But this is essentially saying that it's bounded by this, right? This is E1 plus epsilon E2.
Right.
So, but we know it's convex, so it's going to be the
Right.
same. I mean, I'm just saying this may be a trivial bound, I guess.
Right. I was wondering like how much sharper would the bound be? Like when you say the upper bound and going through the proof.
That I don't know.
Okay.
Yeah, but it can be done. You can try to do the computation. I think if you fix an epsilon, at least my guess is that for large D, you will get a bound better than this.
Okay.
Sufficient large D.
Okay. Thank you.
Does that like a reasonable guess?
Yeah. Thank you.
But for small d, I don't think it's going to be doing better than just this one.
Okay.
Yeah.
Thanks.
Yeah.
Yeah, thanks for giving the talk so early in the morning your time. We all appreciate it. And
No problem.
yeah.
Yeah,
thank
I
you.
got to my office in order to have better internet.
Oh wow, okay. Yeah,
Actually, when I was at home, I couldn't see all the lectures in a smooth way. Basically, it's very lagging.
So I don't know. Yeah, I don't know if you know that all the talks are online on YouTube. Actually,
Yeah,
so you
I
can-
usually watch them afterward.
Oh wow, okay. Yeah, well, thanks for following along with us then. So.